Hi everyone, my name is Luis, and this is Hades Aerospace new video. Today, after 2 years of activity on the channel, I am back with a new series of updates. We have Thrust Vector Control MINERVA-1, a new flight computer TRAPPIST-1, and a new official rocket, Centauri. Today in particular we will talk about the TVC, acronym of Thrust Vector Control, its functionality, dimensions, and structures. And of course, we will also talk about the TRAPPIST-1 flight computer. Thrust vector control are control system mainly used to direct the thrust of the propeller in order to stabilize the vector in a fixed position. Minerva has a circular design that has an external diameter of 97 mm and is designed to support a 38 mm motor, that in my case is a Cicerone, that has an average thrust of 164 N and has two 15 kg of high torque servo motors. The TVC consists of two servos, X and Y, by a central body for the passage of the engine and by two rings blocked by joints to allow movement. The TRAPPIST-1 flight computer has been designed to have a micro SD card support, such as a data logger, a 6-axis gyroscope accelerometer MPU 6050, a RGB LED, a buzzer, a BMP 180 barometer, and the brain of the whole flight computer, that is a ATmega 328P. An Atmel AVS chip with 32 pin, 32 KB of flash, 2048 byte of RAM, and 1024 byte of EEPROM, and 20 MHz of frequency. The PCB is 1.6 mm thick and it is 150 times 75 mm in size and will be powered by a 7.5 volt 2500 mAh LiPo battery. The flight computer is used to obtain the data regarding the flight of the Centauri rocket, in addition to detecting the inclination of the rocket thanks to the gyroscope, and consequently it is also capable of maneuvering the TVC. Obviously, the name TRAPPIST-1 derives from the star located in the constellation of Aquarium, and an Easter egg cannot be missing in the back of the PCB. El Psychangro. Now let's talk about the PID, the proportional integral derivation. Okay, there is a lot to say here, as the whole rocket control system is based. The PID is a control algorithm that is used to stabilize the system thanks to some parameters. From a mathematical point of view, the PID is a dynamic system that precedes the error signal, which is equal to the difference between the reference value of the variable being controlled. The PID is formed by three control terms, precisely the proportional, the integrated, and the derivative. The proportional provides an output proportional to the error, and the resulting error is multiplied by the gain Kp, relative to the proportional, to obtain the output. The speed over the response increases as the constant Kp increases. The integral I integrates the error over a period of time until it reaches 0. Holds the value at the final control device where the error becomes 0. The speed of response increases by decreasing the integral gain Ki. Their derivative d, since the integral controller does not have the ability to predict the future behavior of the error, it reacts normally once the set point has been changed. The derivative solves this problem by anticipating the future behavior of the error. Its output depends on the rate of the change of the error in respect to time, multiplied by the derivative constant Kd. The PID controller is structured by the sum of all three control terms to then obtain the error output, for then repeat the calculation in a loop for each input value in the time interval. In our case, the angles of the gyroscope. To set the value of proportional integrated derivative, you can resort to use of computer simulation, such as the one I used of Cygnus Aerospace system, very accurate to describe the probable trajectory of your rocket, and in my case, the value of Kp, Ki, Kd are 0.15, 0.06, and 0.030. For example, let's say that the rocket starts in a vertical direction at 0 degrees, which is impossible in my case, but fantasize is always nice. And a gust of wind, its tilt is by 2 degrees. The flight computer, but precisely the MPU 6050, detects this inclination, and consequently sends the input to the servo motors, which will move in the opposite direction to the inclination in order to stabilize the rocket in its initial position, or at least try to do so. It was a real challenge to design all this stuff, and above all conceptually, since to do it you have to study enough. So, but after a series of design and failure in 3D printing, and also on board electronics, I managed to come up with something affordable, or at least I hope so. I totally threw and redone a lot of things, not to mention the code that was pretty hell, with 12 hours of debugging, and not bad if you start computing from zero, like me. That my first TVC in 2020 quarantine were made oh Jesus, were made of plastic and cardboard, and then I evolved to something a little more like a TVC, but fully arranged. And today I'm here with something different, but it's just a starting point. Same thing, obviously, with the PCB. It goes without saying that the first was complete failure. And for this video, it's all. There will be other updates regarding the Centauri rocket and the igniter for the motor and the parachute ejection system. So stay tuned in my Hades Aerospace Instagram profile, and remember, nothing is impossible in the universe, unless laws forbid it. Goodbye.